Alright, so channel capacity, how many bits can you send? So Nyquist theorem says that if your bandwidth is B, your data rate has to be less than or equal to 2B. Your bit rate would be twice the baud rate. So here is the coding: 0, 1, 0, 1, 0, 1, 1 bit per baud, right? So the baud rate, now let's see. No, actually that's why I drew this. Hold on. This is 1 bit. This red thing is 1 bit. So the bit rate is twice the baud rate, or half the baud rate, whatever. So the thing is, here, this is 1 baud, this is another baud, 2 baud that make a bit in this coding. And this is another bit, and so on and so forth. But you could do, instead of by level, you could do 4 levels. So this could be 0, 0, 0, 1, 1, 1, 1, 0, and basically what you would do is you would put the numbers so that there is only 1 bit changes at a time, just like we did in that phase diagram. You wouldn't just put 0, 0 here and then 1, 1 there, because it is quite possible for us to mistake that from that for that one in the levels, right? In this case, we are just talking amplitude. So you could do 2 bits at a time, and then you will have 4 levels, 1, 2, 3, 4 levels, and so on and so forth. In this case, you would be able to send, now, okay, here's the thing, I'm sorry, I'm a little bit confusing you, but basically, so there are 2 bits here, 2 bits here, 2 bits here, 2 bits here, right? And then 2 bits, 2 bits, 2 bits, 2 bits, and so every pulse is a 2 bit, right? And this is a baud. Baud is, let's say every pulse is 1 second, so then it is 1 baud per second, but there are 2 bits per second. So the bit rate is twice the baud rate, right? But what is a cycle? Now you notice that if you were to send this signal, the wire that you're going to send it through, it doesn't see any bits and bauds. What it sees is cycles, and here is a cycle. It starts from here 0, goes there, goes 0. Then it starts from there and goes there, right? So it's like a sine wave or something, right? And that cycle is how much? Is basically, if everything is 1 second, then the cycle is 1, 2, 3, 4, 5, 6, 7, 8. 1 cycle per 8 seconds. We have 2 bits per second, but 1 cycle of it. So basically, your capacity is 4 times the bandwidth. Now, so the bandwidth is 1/8 of a cycle per second, right? And 4 times that would be 1/2 of a bits per second, 2 bits per second. Capacity is 4 times. So the cycle is 1, 2, 3, 4, 5, 6, 7, 8. 8 second. Cycle is 8 seconds long. The bits are half second long. So we are sending 2 bits per second, but we are sending only, okay, there is a slight problem here. And the problem is that this is not the right cycle. So wire will not see this. What wire will see is the worst case cycle. So this frame is very good, but in the worst case, you could be sending things much faster, which is that you could be sending this, let's say, whatever this is 0, 0, followed by whatever this is, let's say 0, 1 or something like that, whatever, right? And then 0, 1, 0, 1. So your cycles will be much smaller. Okay? So think about that cycle, and that cycle will not be 8 seconds, that cycle would be just 4 seconds. 2 seconds low, 2 seconds high, 2 seconds low, 2 seconds high, 2 seconds low, 2 seconds high, right? Sorry, 1 second low, 1 second low, 1 second high, so it will be 2 seconds. per cycle. So it is half cycle per second and 2 bits per second. That is 4 times. So the bit rate is 4 times the cycle rate. Right? Cycle rate is called hertz. Okay? So you have half cycle per second means half hertz, and you are getting 2 bits per second. Right? So whenever somebody presents your coding, you have to take the worst case cycling in that one, and worst case in that one, how fast the things will change, and that is what is called bandwidth. Now here is the thing, lot of time computer scientists misuse the word bandwidth to mean the bit rate. But bandwidth is actually more coming from the analog days, and that is actually the cycle rate, the hertz rate, hertz. So the bandwidth is hertz. Okay, so you measure, and the wire really cares for the hertz. So what happens if you take a wire, its capacity is limited by how many cycles can go through it. Okay, so that's why we have this Cat 4, Cat 5, Cat 6, Cat 7, Cat 8, Cat is category, Ethernet cables. The higher the category, they have a higher cycles that can go through, higher number of megahertz that can go through it. Okay, so the wires are measured by the hertz. The electronics which is at the source and destination is measured by baud, and what you are interested is measured by bits. And there are 3 people involved here: the sender, the user, the sending electronics, and receiving electronics. So the electronics, the wire, and the user. Electronics is limited by what? Again, we just said, Somebody listen. What electronics is limited by baud, and the wire is limited by hertz, and the user is interested in bits. And there is no relationship in the sense that can you have 2 bits per hertz? Answer is yes. We just saw an example here, 4 bits per hertz. Right? Can you have half bits per hertz? Yes. There are coding which give you only half bits per hertz. Okay? Because in those cases, you really want no errors whatsoever. So you are very careful. Okay? You get half bits per hertz means you send 2 cycles per bit. Okay? And similarly for the bauds. And so the bauds and bits. Now bauds and cycles may have some relationship because you cannot have, so let's say I think you can have 2 bauds per cycle, but you cannot have, well, maybe you could have 2 cycles per baud. Yeah, you could have that too. So basically, one is not more than the other. Basically, it depends on the designer to put the relationship together. So when you design these codings, you have to decide how much baud, how much electronics you want to put on the electronics, what kind of wire you want to use, and what you get out of it. So anyway, Nyquist theorem says that you cannot get more than 2 times the bandwidth if you use bi-level coding. If you use M-level coding, you cannot get any more than 2 times the hertz rate times log 2m. Log of m base 2. M is the number of levels. Okay. Now I just gave you an example of 4 level, but you could have higher levels. In this 4 level, the main confusing thing is that this looks like a cycle. I should probably draw another diagram with the worst case cycle for this coding. Okay. And that diagram would be where you are just jumping between high and the low. And so the cycle would be much smaller. Yeah.
What determines a channel in that case?
Channel. What is a channel? So basically, generally we use channel for the whole thing. Send all the way from sending electronics to the wire to the receiving electronics. The whole thing is called a channel, right?
Can you have multiple channels?
Yeah. So you could do multiple channels. You could have 3 wires.
Oh, but it's
4
one
wires.
channel per wire?
No, you could have 1 channel per 2 wires. See, thing is, this is another domain, okay? So the question is, generally, you will have depending upon the way you design it, you could have 2 wires and 1 channel. Because you will have positive and negative. So to determine that, you will need 2 wires, right? And then, for example, Ethernet wire has 8. Ethernet cable has 8 wires in it. Right? It's 4 channels. Ethernet cable has 4 channels, and they're all in parallel. All right. So now we go to another theorem, Shannon's theorem. And Shannon says that depending upon how much noise you have, you cannot talk too much. So right now we are, I can give a very fast lecture and you will understand. But if it was, let's say, a fair with a lot of people, talking to each other and going around, then I couldn't talk very fast. Because if I talk too fast, you won't understand anything, right? So the bits that can be sent also depend upon the noise. And his formula is that if you take signal S and the noise N, measure them, and then take the ratio at 1, take log base 2, and multiply by the bandwidth, that is the maximum data rate you can get, maximum bit rate you can get. So here's an example. Let's say phone wire. Now the phone wire that we use for phones, that is really a poor wire. It was designed in very old days, and it does have a frequency. It has a limit of 31 hertz, 3100 hertz. Okay, 3.1 kilohertz or 4 kilohertz at most. If you send any more than that, it cannot take it. So 3100 hertz is the phone wire bandwidth. And now if you are going to use it where there is a noise such that the signal to noise ratio is 30 dB. Now you have to understand by now dB. I will be using dB now left and right. Now dB is what? Does anybody know what dB stands for? Decibel. And decibel is 10 times in upon out or something like that, right? So that's what it is. This is 10 times that. So 3 is the 10 times log of base 10. Now you have to keep track of that base also very clearly. When we defined the bell, it was log base 10, but we are using log base 2 for both Nyquist and Shannon. Right? So log base 10 signal to noise ratio 30 means signal to noise ratio is 1000. Okay. Now people who work in this field, they just get used to this kind of translations. In their mind, log base 10, if somebody says 10 dB, they know it's the ratio is just 10. They say 20 dB, the ratio is 100. Say 30 dB, the ratio is 1000. 40 dB, ratio is 10,000. They just get used to that multiplication. You will get used to too by the end of this course. But basically, right now you have to calculate what is 30 dB. Other people don't think. People who are experts, they know 30 dB is a factor of 1000. Okay? So 30 dB is a factor of 1000. This is how. Alright, so basically the capacity is log base 2 1 plus S upon N. S upon N is 1000, and therefore you do all this math and it comes out 30 kilobits per second. 30.894 kilobits per second. Yeah.
How can we measure the noise?
How can you measure the noise? Yeah, so basically if you had a oscilloscope, you can see the noise. Basically, I mean, you can, whatever signal you receive, you subtract out the perfect sine wave from that and you get the noise. So you can see the noise in oscilloscopes.
So noise will be measured in what kind of unit?
Same unit as signal. So signal you measure in watts or, watts. And you measure the noise in watts, take the ratio. Right? So actually what we will do is we will not be using watts. Just when I said watts, I said, well, we really don't measure with watts. What we do is we measure everything in the unit is coming up in a minute. So I'm going to hold on to that one. Okay? What we do is we measure everything with respect to 1 milliwatt. So if you have 1 watt of power, with respect to 1 milliwatt, it is 1000 times. Right? So it is 30 dBm. So this is how the power is measured. Somebody says, well, the power is 30 dBm. That M is for milliwatt. dB is for decibel. So 30 dBm means 1 watt. Now, you should be quick and figure out if 30 dBm is 1 watt, how much is 40 dBm? Can somebody do this quick in their brain? 40 dBm would be 10 watts. Good. All right, so you will get used to this multiplication and log scale working, soon. So they always work in log scale. They don't use watts. They just use dBms.